Everything you were taught about gravity fits into 2 lessons. Lesson 1. Gravity is a force. Newton, the apple, the moon. Lesson 2. Gravity is geometry. Einstein, curved space, bending starlight. But here is what nobody told you. The book is missing its final chapter. Every other force in nature has shown us its particle, lights, caught. The strong forces, caught in 1979. The weak forces, in 1983. Gravity's was named in 1934, and it has never been seen. Yet if the theory is right, 4 of them pass through your bedroom every second, and in 4.5 billion years, the entire Earth has stopped almost none of them. One of the great physicists of the last century argued the universe may be built to keep them hidden forever. By the end of tonight, you will know exactly what is missing from the gravity you were taught, and whether anyone will ever catch it. Before we begin, if questions this large, taken this slowly, are how you like to drift off, a quick like or subscribe really does help the channel grow. It is a small thing for you, and it means the world to me. Now, let's ease in. There is a page missing from every physics textbook you were ever handed, and tonight we are going to find out what was supposed to be printed on it. Let's start with what was there. Think back to the first time anyone explained gravity to you. It was probably a story in 2 chapters, and the odds are good that you can still recite both of them. Chapter 1 belongs to Isaac Newton. The year is 1687. The book is the Principia, and the idea is beautiful in its bluntness. Gravity is a force. Every object with mass pulls on every other object with mass, everywhere, always. The pull gets stronger as the masses grow, and it fades with the square of the distance between them. Double the distance, and the pull drops to 1/4. The same rule that drops an apple holds the moon in its orbit, and Newton showed, with nothing but geometry and patience, that these are not 2 phenomena, but one. For more than 2 centuries, that single sentence ran the universe. It steered ships, predicted eclipses, and found the planet Neptune sitting exactly where the mathematics said an unseen mass had to be. Chapter 2 belongs to Albert Einstein. In November of 1915, he replaced the force with something stranger and, somehow, even more elegant. Gravity, in general relativity, is not a pull at all. It is geometry. Mass and energy bend the fabric of space and time around them, and everything else simply follows the straightest possible path through that bent fabric. The apple does not feel a tug. The apple coasts, freely and peacefully, along a curve that the Earth's mass has carved into time itself. Matter tells spacetime how to curve, and spacetime tells matter how to move. And this chapter, too, came with receipts. It explained a stubborn wobble in Mercury's orbit that Newton never could. It predicted that starlight would bend around the sun, and in 1919, during a total eclipse, the light bent by precisely the predicted amount. A century later, its predictions still land, with a precision that borders on the unreasonable. The clocks in the satellites above your head run fast by 38 millionths of a second every day, exactly as Einstein's equations demand. And if nobody corrected for it, the map on your phone would drift by kilometers within a single day. 2 chapters. A force, then a geometry. A genius, then another genius. It is a complete story, satisfying, symmetrical, and finished. That is how it was taught to you, and that is how most people carry it for the rest of their lives. But here is what they left out. The book is not finished. There is a 3rd chapter, and it has never been written, because for 100 years, the finest minds in physics have tried to write it and failed. Not for lack of ideas, for lack of a single, stubborn, almost comically elusive piece of evidence. And once you see the shape of that missing chapter, you will understand why the title of tonight's journey is not an exaggeration. Everything you were taught about gravity is true, and everything you were taught about gravity is incomplete. To see the gap, you only have to look at what happened to every other force in nature during the 20th century. There are 4 fundamental forces. Gravity is one. The other 3 are electromagnetism, which runs everything from light to chemistry to the nerves firing gently in your body as you listen to this. The strong nuclear force, which welds the cores of atoms together, and the weak nuclear force, which lets stars burn and certain atoms decay. And in the early decades of the 20th century, physicists discovered something astonishing about those 3. Underneath their smooth, continuous appearances, they are grainy. Zoom in far enough on a beam of light, and it stops being a wave and becomes a hail of individual packets, particles of light called photons. The strong force, examined closely, resolves into carriers called gluons. The weak force resolves into heavy carriers called the W and Z bosons. Every force, it turned out, is a kind of conversation, and every conversation is carried by messengers. The messengers are particles. This is the quantum revolution, and it is, without competition, the most precisely confirmed set of ideas human beings have ever produced. Now ask the obvious question, the question a child would ask, which is usually the question physics most needs to answer. If electromagnetism has the photon, and the strong force has the gluon, and the weak force has the W and the Z, then what does gravity have? Theory has an answer ready. It even has a name, and the name has been waiting since 1934. The graviton, the quantum of gravity, the individual grain of the gravitational field. If gravity plays by the same rules as everything else in this universe, then the smooth curvature Einstein described is an approximation, the way a photograph of the ocean from an airplane is an approximation, and up close, the ocean breaks into individual waves and droplets. Up close, in this picture, gravity breaks into gravitons, and because Einstein taught us that gravity is not a thing sitting in space, but the shape of space and time themselves, the implication comes with a shiver attached. If gravity is made of gravitons, then space-time is made of gravitons. The stage itself is built from particles, the floor under your bed, the distance between you and the wall, the seconds sliding past you right now as you settle in. All of it would be, at the very bottom, a swarm of quanta, the way a sheet of steel is secretly a lattice of atoms. Every serious attempt to write the 3rd chapter of the gravity book needs this particle, or something that plays its part. String theory needs it, and in fact predicts it whether you ask for it or not. Loop quantum gravity needs the graininess it represents. Every road to what physicists call quantum gravity, the long-sought union of Einstein's geometry with the quantum world, runs through this one hypothetical grain. And here is the fact that should keep you comfortably unsettled for the next 2 hours. In the 90 or so years since the graviton was named, nobody has ever detected one. Not one. Not directly, not indirectly, not once. The photon was named and then caught. The gluon was predicted and then photographed, in a manner of speaking, in the debris of particle collisions in 1979. The W and Z bosons were predicted and then produced, on demand, in 1983. The graviton was named in 1934, and in all the decades since, it has remained exactly what it was on the day of its christening. A word. A beautifully motivated, mathematically respectable, completely unobserved word. You might assume this is simply a matter of building a better instrument and waiting. That is how it always goes, isn't it? And this is where the story turns into something stranger than a tale of engineering patience. Because in 2012, one of the great physicists of the 20th century stood in front of a room of his colleagues and made a careful, quantitative argument that the graviton may be undetectable in principle, not hard to see, not expensive to see, impossible to see, with the laws of physics themselves supplying the censorship. Every route you take toward a single graviton, he argued, gets blocked, and the blocks are not bureaucratic. One route ends with your detector collapsing into a black hole. Another ends with the vacuum of empty space itself shattering before the measurement can finish. It is as if the universe were structured to keep its own foundations out of sight. So the question tonight is really three questions, stacked inside one another like nesting dolls. The smallest one, what would it actually take to catch a single graviton? The middle one, why does every attempt seem to slam into a wall built, strangely, out of the very physics the graviton would explain? And the largest one, the one we will hold on to until the very end and answer plainly, what exactly is missing from the gravity you were taught? And is that missing chapter a page humanity will someday write, or a page the universe has decided no one gets to read? By the end of tonight, you will know the honest answer, and I will tell you now that it is more hopeful than the middle of this story is going to feel. Along the way, we will shrink to a billionth of the width of a proton and inflate a particle accelerator until it brushes the nearest star. We will meet an 88-year-old heretic with a gentle smile, a 10-ton cylinder colder than the space between galaxies, and a number so absurd it will follow us through the whole night like a signature at the bottom of every page. But it starts smaller than any of that. It starts with a simple, almost embarrassing question about the nature of light, asked at the very beginning of the 20th century. Because before we can appreciate why gravity's particle is missing, we need to understand how anyone ever proved that a force has particles at all. And that story, the story of how the photon went from heresy to textbook, contains a secret flaw, a hole in the logic that almost nobody talks about, which will come back at the end of tonight to change the meaning of everything the new experiments are trying to do. The other three forces showed their receipts. Let's go and look at how they did it. The idea that a force could be made of particles did not arrive as a triumph. It arrived as an embarrassment, and the person it embarrassed most was the man who proposed it. Picture physics at the close of the 1800s. Light had been settled, or so everyone believed. James Clerk Maxwell had shown that light is an electromagnetic wave, a ripple of electric and magnetic fields rolling through space, and the wave picture explained essentially everything anyone could measure. Waves interfere. Waves diffract around corners. Light does both, beautifully. The matter seemed closed. But there was one stubborn little phenomenon that refused to behave, and it lived in the most ordinary of places. A polished metal surface. Shine light on certain metals and electrons pop out. This is the photoelectric effect, and by all rights, it should have been a footnote. The wave picture made a clear prediction about it. A wave carries energy continuously, spread across its whole front, so a brighter light should eject electrons with more energy, and even a dim light, given enough time, should slowly rock an electron loose, the way small waves eventually work a boat free of its mooring. That is not what happens. What happens is stranger and much more abrupt. Below a certain frequency of light, a certain color, if you like, nothing comes out at all. Ever. You can make red light as blinding as you please, and shine it on the metal for a year, and the electrons simply will not budge. But cross the frequency threshold into bluer light, and electrons leap out instantly, even when the light is almost too faint to see. Brightness controls how many electrons emerge. Only frequency, only the color, controls whether they emerge and how energetically. It is as if the metal cared nothing for the total amount of energy arriving, and cared only about the size of the individual portions. In 1905, a 26-year-old patent clerk named Albert Einstein, the same man whose second chapter of the gravity book was still a decade in his future, took that hint at face value. Suppose, he said, that light is not a continuous wave, but a stream of discrete packets, each one carrying an energy set by the frequency. Bluer light means fatter packets, An electron cannot save up energy from many small packets. It absorbs one packet, whole or nothing. If the packet is too small to pay the electron's exit fee, no quantity of packets will ever add up, just as a vending machine that takes only a single coin will not accept 1,000 pennies. Cross the threshold, and one packet alone is enough, which is why even the faintest blue glow ejects electrons immediately. Those packets would eventually be named photons, and here is the part they rarely tell you. The physics establishment hated the idea. Not doubted it, hated it. Max Planck himself, whose work had planted the seed, apologized for Einstein when nominating him for the Prussian Academy, asking that his colleagues not hold the light quantum against a man who was otherwise so promising. Robert Millikan, one of the great experimentalists in America, spent a decade trying to prove the packet picture wrong, measured the photoelectric effect with exquisite care, confirmed Einstein's equation in every detail, and still called the underlying idea reckless. It took nearly 20 years, and a further experiment in 1923, showing that light packets carry momentum and bounce off electrons like billiard balls, before the resistance finally collapsed. When Einstein received his Nobel Prize, it was not for relativity, it was for this, for the photoelectric effect, for the claim that a force field, examined closely enough, is made of countable things. Hold on to that story tonight, and hold on to it tightly, for two reasons. The first is that it became the template. It is the founding legend of quantum physics, the proof, as every textbook puts it, that the electromagnetic field has a particle. Every scheme we will meet later tonight for catching gravity's particle is, consciously and explicitly, an attempt to stage a new photoelectric effect, with gravity playing the role of light. The second reason is one we will keep sealed until near the end of the night. The legend has a flaw. The photoelectric effect, it turns out, does not quite prove what generations of students were told it proves, and the gap in that old argument will fall like a shadow across the shiniest new Graviton experiments of the 2020s. Remember the vending machine. We will come back for it. Once the photon was accepted, the 20th century did something remarkable. It took the idea and ran a production line with it. Quantum field theory, the mature form of the quantum revolution, repainted the entire physical world in one consistent scheme. In this picture, the fundamental things in nature are not particles at all. They are fields, invisible, space-filling media, one for each kind of particle, and what we call a particle is a localized ripple in its field, a knot of vibration that holds together and travels. An electron is a ripple in the electron field, a photon is a ripple in the electromagnetic field, and a force, in this language, is what happens when the ripples of one field disturb another. Two electrons repel each other because they are constantly exchanging photons, messengers carrying momentum back and forth between them, the way two skaters drifting apart on ice could push each other away by tossing a heavy ball back and forth. The force is the conversation, the messenger particles are the words, and the scheme kept cashing checks. The strong nuclear force, the glue holding atomic nuclei together against the electrical repulsion of their protons, was predicted to have its own messengers, gluons, and in 1979, at an accelerator in Hamburg, collisions began producing telltale three-pronged sprays of debris, and the third prong was the fingerprint of a gluon caught in the act of being radiated. The weak nuclear force, the shy interaction that lets the sun fuse hydrogen and lets unstable atoms decay, was predicted to have three heavy messengers, the two W bosons and the Z. In 1983, at the Kern laboratory beneath the border of France and Switzerland, they were manufactured directly, on demand, in proton collisions, with masses landing where theory had pointed. Prediction, then production, then measurement, then precision. In the decades since, the properties of the photon have been checked to better than 1 part in a trillion. The pattern held every single time a force was put to the test. Field, ripple, messenger, receipt. Now stand back and look at the scoreboard, because the scoreboard is the point of this whole part of our story. Electromagnetism, messenger found, receipts filed, precision beyond reproach. Strong force, messenger found, 1979. Weak force, messengers found, 1983. Gravity, silence. And notice something almost comical in the timing. The graviton is not the newest name on the list. It is one of the oldest. In 1930, before the gluon or the W boson had even been imagined, a physicist named Leon Rosenfeld was already publishing the first attempts to apply quantum rules to the gravitational field. In 1934, two Soviet physicists, Dmitry Blokhintsev and F. Galperin, wrote down the natural analogy: if light has the photon, gravity should have its quantum, and they gave the hypothetical particle its name, graviton. In 1939, Marcus Fiers and Wolfgang Pauli worked out, in full mathematical detail, what the theory of such a particle must look like, and their construction still stands today as the template for what a graviton has to be. Understand what this means. The graviton was named before the neutron was barely settled science, before the transistor, before the discovery of the expanding universe was a decade old. Physicists who were born, spent entire 50-year careers, and died, all lived inside the window in which this particle has been predicted and never seen. Every other messenger on the board went from hypothesis to detection within a few decades. The graviton has been waiting for nearly a century, and it is not waiting because nobody looked. There is a temptation, hearing this, to shrug and say that gravity is simply different, that maybe it does not need a particle, that maybe Einstein's smooth geometry is the final word, and the analogy with the other forces is a false scent. It is an honest thought, and remarkably, we will meet a world-class physicist tonight who took a version of it seriously. But before you settle into it, you should know that the case for the graviton is not a case built on tidiness or on wishful symmetry. It rests on some of the hardest arguments in theoretical physics, and on one measurement, made in 2017, involving two dead stars and a flash of gamma rays, that pinned down the properties of gravity's messenger with an accuracy that would be the envy of any particle hunter. Because here is the strange thing about this missing particle. We have never seen it, and yet we know, in astonishing detail, exactly what it must look like. We know its mass, we know its spin, we know its speed to 15 decimal places. The wanted poster is complete in every detail except the photograph. So before we watch the universe slam its doors on every attempt to take that photograph, let's do something a little audacious. Let's build the graviton on paper, property by property, and see what kind of creature physics has been chasing all this time. Because the moment you see what the graviton would have to be, you will also see, with a slow, settling clarity, what it would mean. It would mean the stage you are lying on right now is made of actors. It sounds like a contradiction to say that physics knows everything about a particle it has never seen. But this is one of the quiet powers of theoretical physics, the ability to corner a hypothesis so thoroughly that its properties are fixed before any instrument confirms it exists. The neutrino was described in loving detail for 26 years before anyone caught one. The Higgs boson was characterized for nearly half a century before it appeared. The graviton has been cornered longer and more completely than either. So let's build it, one property at a time, and let each property sink in slowly, because each one is going to matter later tonight when we watch the universe defend it. Property 1. The graviton is massless, or so close to massless that the difference could never matter. This is not a guess. It follows from something you can observe from your own window. Gravity reaches across the universe. The force between two masses fades with distance, but it never cuts off, and that unlimited range is the signature of a massless messenger. In quantum field theory, a force carried by a heavy particle is a short-range force, because a heavy messenger is expensive to send and cannot travel far. The weak force, carried by the massive W and Z bosons, dies within a distance smaller than a proton. Electromagnetism, carried by the massless photon, reaches forever. Gravity holds galaxies together across hundreds of thousands of light-years and bends the paths of galaxies falling toward each other across millions more. A messenger with any appreciable mass could not do that job. Massless then, and therefore, by the rules of relativity, moving always at exactly the speed of light. And on this point, the universe has already been generous enough to run the experiment for us. On the 17th of August, 2017, two neutron stars, the collapsed, city-sized corpses of dead suns, spiraled into each other in a galaxy about 130 million light-years away. The collision shook spacetime, and the ripples of that shaking, gravitational waves, crossed 130 million light-years of universe and swept through the Earth. 1.7 seconds after the gravitational waves arrived, a flash of gamma rays from the same explosion arrived as well. Sit with those numbers for a moment, because they deserve it. Light and gravity raced each other for 130 million years, a journey that began before the first flower bloomed on Earth, and they finished less than 2 seconds apart. Divide it out, and the speed of gravity matches the speed of light to about 1 part in a quadrillion, a 1 followed by 15 zeros. If the graviton exists, that measurement is its speedometer, and the needle sits exactly where a massless particles must. Property 2, and this is the strange one, the one that makes gravity gravity. The graviton has spin 2. Spin is a particle's intrinsic angular character, a quantum property with no perfect everyday counterpart, but you do not need the full machinery to feel what matters here. The messengers of the other forces, like the photon, have spin 1, and spin 1 forces are two-sided. Like charges repel, opposite charges attract, and so electricity can push, as well as pull, can cancel, can shield. A spin 2 messenger carries a force with only one sign. Everything attracts everything. There is no negative mass to cancel against, no gravitational shielding, no way to build a wall that blocks the pull, which is why you can shield a room against radio waves, but no engineer, anywhere, ever, has shielded a room against gravity. That is not a technological failure. It is spin 2 doing exactly what spin 2 does. And a spin 2 ripple has a particular shape. It stretches space in one direction, while squeezing it in the perpendicular direction, then swaps, over and over, a kneading motion. File that image away. In a few parts' time, humanity will build a machine specifically to feel that kneading, and it will become the hero of this entire story. Property 3. The graviton couples to everything. The photon speaks only to electric charge. Neutral particles ignore it. But gravity's source is not some special charge carried by a few particles. Gravity's source is energy itself, in every form, mass, motion, light, pressure, all of it. Nothing is neutral to gravity, because nothing is free of energy. And that universality was proven, in the middle of the 1960s, to be not a choice, but a necessity. Steven Weinberg, one of the architects of modern particle physics, demonstrated a theorem with a conclusion so clean it still startles physicists who meet it for the first time. Any massless spin 2 particle, he showed, must couple to all forms of energy and momentum identically. It has no other option. The mathematics permits nothing else. And a massless spin 2 particle coupling universally to energy reproduces, in the appropriate limit, precisely Einstein's general relativity, the equivalence of gravity and acceleration, the bending of starlight, the whole second chapter of the textbook. Let that sink in. If you had never heard of Einstein, and you simply asked what force a massless spin-2 messenger would carry, the answer that falls out of the mathematics is gravity, curvature, geometry, all of it. The particle and the theory are the same statement in two languages. This is why physicists believe in the graviton, with a confidence that can look, from outside, almost like faith. It is not faith, it is the recognition that the wanted poster was drawn by the laws of nature themselves. There is one more property, though, and it is the one that turns this from a particle physics story into something closer to a bedtime story about the nature of everything. Every other messenger particle is a ripple in a field that lives on the stage of space-time. The photon is a disturbance traveling through space, but the graviton would be a ripple of space-time. Its field is not draped across the stage. Its field is the stage. In the quantum picture, a gravitational field, the curvature around the Earth that holds you against your mattress right now, would be, at the deepest level, a coherent state built out of gravitons, in the same way that the warm light of a candle is, at the deepest level, a flood of photons. And since Einstein taught us that space-time and gravity are one and the same, the conclusion arrives on quiet feet and then refuses to leave. If the graviton exists, then space itself is grainy. Time itself is grainy. The distance from your pillow to the door is a quantity built out of quanta, and the smooth, continuous emptiness you have pictured all your life when you imagine the dark between the stars is a kind of illusion of distance, like the smooth surface of a sand dune seen from far away. Every serious framework for quantum gravity embraces this. In string theory, the graviton is not even optional. It appears automatically, uninvited, as one of the vibration modes of the fundamental strings, and its forced appearance is the main reason string theorists believe their mathematics is on the scent of gravity at all. Loop quantum gravity builds the graininess in from the start, weaving space out of discrete loops whose ripples play the graviton's role. The frameworks disagree on almost everything else, and they have fought for decades, but on this, they are unanimous. If gravity is quantum, something graviton-like must exist, and finding it, or even finding indirect proof of the graininess it represents, would be the single most important experimental result in the history of fundamental physics. It would be the handshake between the two great theories, witnessed at last. Now, before we go hunting, let's be honest about the quarry, because here the story develops its first undertone of unease. Let's actually weigh this particle we have described so confidently. A graviton's energy, like a photon's, is set by its frequency. The gravitational waves that wash over Earth from colliding black holes ring at frequencies near the range of human hearing, around 175 cycles per second, a note in the middle of a piano's range. A single graviton at that frequency carries about 100 billionths of a billionth of a billionth of a billionth of a joule. That number means nothing to human intuition, so let's give it a companion. A single photon of green light, the kind your eye catches effortlessly, by the trillions, every moment your eyes are open, carries roughly 3 trillion times more energy than that graviton. Detectors that count single green photons, one at a time, click by click, have existed for a century. The graviton is not just another small thing. It is trillions of times fainter than the faintest things we routinely catch, and it comes from a force that is itself, as we are about to see, weaker than the other forces by a margin so absurd that writing it down feels like a typographical error. We know its mass, we know its spin, we know its speed to a part in a quadrillion. We know that if it exists, it is the grain of the flaw of reality. What we do not know is whether the universe will ever let us see one. And the first person to ask that question with full mathematical seriousness, rather than simple frustration, was a man who had spent his whole career doing sums other people were afraid of, and who decided, in his 9th decade, to do one more. But to understand the wall he found, you first have to understand just how quiet gravity really is. Come and look at the numbers. They are worse than you think. Here is an experiment you have performed hundreds of times without ever noticing that it is one of the most profound demonstrations in all of physics. Take a small magnet, the kind that holds a photograph to a refrigerator door, and use it to pick up a paperclip from a table. That is the whole experiment. Now consider what actually happened. On one side of that contest was the entire planet Earth. 6 trillion kilograms of rock and iron, the accumulated mass of a whole world, pulling that paperclip downward with every atom it has. On the other side was a trinket, a few grams of magnetized metal you could lose in a draw. And the trinket won, instantly, effortlessly. It did not win by a narrow margin after a strained tug of war. The paperclip snapped upward, as if the planet beneath it were not even there. We are so used to this that we never let ourselves be astonished by it. But tonight, lying still, let yourself be astonished. Gravity is not just the weakest of the 4 fundamental forces. It is weaker by a margin that has no counterpart anywhere else in science, a margin so extreme that physicists themselves regard it as one of the great unsolved embarrassments of their field. Compare the electric repulsion between 2 protons with the gravitational attraction between those same 2 protons. Both forces are acting on the same pair of particles at the same distance, so the comparison is completely fair. The electric force wins by a factor of about 10 to the 36th power. That is a 1 followed by 36 zeros. Numbers like that slide off the mind. So let's slow it down and give it scale. Count every grain of sand on every beach and in every desert on Earth. You would reach roughly 10 to the 18th power, a 1 followed by 18 zeros. Now imagine that every one of those grains of sand contains, inside itself, an entire Earth's worth of new beaches and deserts, and count every grain of sand in all of those. Now you are approaching 10 to the 36th. That is not a gap. That is a chasm the size of arithmetic itself, and nobody knows why it is there. Physicists call the mystery of gravity's extreme feebleness the hierarchy problem, and it stands to this day as one of the deepest unanswered questions in science, a question so stubborn that entire theories, extra dimensions, new symmetries, whole invisible worlds have been invented largely to explain this single lopsided ratio. The weakness we are about to struggle against all night is not a technicality. It is itself one of the universe's unexplained decisions. And keep that particular number, 10 to the 36, somewhere comfortable in your mind tonight, because I will tell you now, as a small promise, that it is going to come back. It is going to come back in a different costume, in a completely different corner of this story, measuring something that has nothing to do with the strength of forces, and when it does, you may feel the small chill of recognizing a signature. The same absurd number keeps showing up in this subject, and by the end of the night, you will be entitled to wonder whether that is a coincidence. Why, then, does gravity feel so mighty? Why does gravity, the hopeless weakling, pin you to your bed and hold the moon in the sky, while the incomparably stronger electric force does neither? The answer is that gravity cheats, in 2 ways. First, it never cancels. Electric charge comes in positive and negative, and the universe is scrupulously balanced between them. So on any large scale, the electric force neutralizes itself into silence. Your body is electrically neutral to better than 1 part in a billion, and so is the Earth. Gravity's charge is energy, and energy has only one sign. Every atom adds, nothing subtracts. Second, gravity accumulates without limit. Pile up more and more matter, and the pull only grows. So on the scale of planets and stars, the weakling, unopposed and endlessly accumulating, rules the universe, while the Titan, perfectly self-cancelled, hides inside atoms. It is one of nature's finest ironies. The strongest forces bind the small, the weakest force governs the whole. But now translate this weakness into the quantum language we built in the last part, and you will see the hunting problem take shape. In quantum field theory, the strength of a force appears as a number called a coupling constant, which sets the probability that a particle will emit or absorb one of the force's messengers. When an electron travels through the world, it emits and absorbs photons constantly, casually, the way a person walking through rain meets raindrops, because the electromagnetic coupling is healthy and strong. The gravitational coupling between individual particles at everyday energies is suppressed by that same monstrous factor. Ask how often an electron emits or absorbs a graviton, and the honest answer is essentially never. You could watch a single electron for the entire age of the universe, 13.8 billion years, and you would not expect to see it exchange a single graviton with the world around it. The conversation that gravity holds with matter is real, but at the level of individual words, individual messengers, it is the quietest conversation in nature, sparser than one word per lifetime of the cosmos. There is, however, a loophole written into the fine print, and the fine print is where our story is headed. The gravitational coupling is not actually constant. It grows with energy. Collide two particles gently, and gravity is a spectator, mute and irrelevant. Collide them harder, and gravity's voice grows, quadratically, with the violence of the encounter. Push the collision energy high enough, and there is a threshold where the gravitational coupling finally catches up with the other forces, where gravity at last speaks at normal volume, and producing gravitons becomes as routine as producing photons. That threshold has a name. It is the Planck energy, part of a family of natural scales that Max Planck wrote down, remarkably, back in 1899, before quantum theory even existed, simply by combining the speed of light, the strength of gravity, and his own new constant into quantities with the dimensions of energy, length, and time. Planck noticed that these units were universal, built from nature's own ingredients rather than human conventions, and he suggested, with what turned out to be spectacular understatement, that they might be significant. So, how much energy is the Planck energy? Here is where the story turns quietly comic. The Planck energy is about 2 billion joules. 2 billion joules is not, by human standards, an exotic amount of energy. It is roughly the kinetic energy of a loaded freight train rolling at full speed. It is the energy released by exploding about half a ton of TNT. It is the electricity a typical home draws in 2 or 3 weeks. You have personally been near 2 billion joules many times. Standing on a platform as an express train passes, you have watched a Planck energy glide by, wrapped in steel and completely harmless. The catch, and it is everything, is concentration. The train's 2 billion joules are spread across hundreds of tons of metal, shared among more particles than there are stars in the observable universe many times over. To wake gravity's quantum voice, you need that same 2 billion joules loaded into a single pair of colliding particles. All of the train's fury, compressed into 2 protons, meeting head-on. That is the price of admission to the regime where gravitons are freely made. And to give you a first taste of how far away it is, consider the most powerful particle accelerator human beings have ever built, the Large Hadron Collider, a ring 27 kilometers around, buried beneath the French-Swiss border, the most complex machine in the history of our species. Its record-breaking collisions carry about 2 millionths of a joule, 2 millionths, against a target of 2 billion. The gap is a factor of 1,000,000 billion, 15 orders of magnitude, the ratio between the width of a human hair and the distance to the nearest star beyond the sun. Let the shape of the problem settle in, because it is the shape of everything to come. The graviton is not hiding in some unexplored corner of accessible physics, waiting for a cleverer filter or a longer exposure. It lives behind a wall of weakness, 36 orders of magnitude high, with a doorway, the Planck energy, that sits 15 orders of magnitude beyond the strongest machine humanity has ever constructed. Any honest plan to catch one must either scale that wall by brute force, and we will see in a little while what brute force would literally require, or find some way around it that nobody has thought of yet. In 2012, one of the 20th century's most original physicists decided to survey every route up that wall, one by one, with pencil and paper, and no mercy. What he found was stranger than mere difficulty. He found that the universe appears to have opinions about this particular climb, and to appreciate what he found, you need to meet the man, because the messenger matters here. This was not a crank on the margins, not a contrarian chasing headlines. This was the man who, 60 years earlier, had helped build the very quantum theory of forces we have been describing all night. A man whose entire life had been an argument that no calculation is too audacious to attempt. His name was Freeman Dyson, and in his 89th year he stood up in front of the world's mathematical physicists and asked, politely, whether the particle everyone was looking for could ever, even in principle, be seen. Freeman Dyson was born in England in December of 1923, which means he was born into a world where the Graviton did not yet have a name, and he would live long enough to explain, better than anyone before him, why it might never earn a face. He was the kind of child who read mathematics books for pleasure and calculated for the joy of it, and the kind of young man whose gifts were noticed early and put to grim use. At 19, in the middle of the Second World War, he was pulled into the operational research section of Britain's Bomber Command, where his job was statistics in the service of survival, analysing which bombers came home and which did not. He spent the war doing honest arithmetic about terrible things, and he emerged with two convictions that would run through the rest of his 96 years. First, that calculation is a form of truth-telling, that you do not really understand a claim until you have followed its numbers all the way to the end. And second, that authority deserves arithmetic rather than deference, because he had watched confident institutions be confidently wrong. After the war came Cambridge, and then, in 1947, a fellowship carried him to Cornell University in America, into the middle of the greatest crisis and triumph of 20th century physics. Quantum electrodynamics, the quantum theory of light and matter, was being rebuilt, and its two chief architects could not understand each other. Julian Schwinger had constructed a version of the theory that was mathematically imposing and nearly impenetrable. Richard Feynman had invented a completely different approach, intuitive, pictorial, built from little diagrams of particles exchanging messengers, the very diagrams that would later carry his name and fill every blackboard in every physics department on Earth. The two methods looked like different sciences. In the summer of 1948, Dyson crossed America on a Greyhound bus, and somewhere in the long, flat middle of the country, with no desk, no library, and no supervision, the pieces fell together in his mind. He saw that Schwinger's machinery and Feynman's pictures, along with an independent formulation by the Japanese physicist Sin Ichiro Tomonaga, were one and the same theory, wearing three costumes, and he proved it. He was 25 years old. The proof made the modern theory of forces usable, teachable, and trustworthy. It is the framework, you may notice, behind everything we said in Part 2, the fields, the ripples, the messengers. When we described how forces work, we were speaking a language that Freeman Dyson helped make coherent, and he did it before he had a doctorate. He never bothered to get one, in fact. And the Institute for Advanced Study in Princeton, the home of Einstein and Gödel, hired him anyway, and kept him for the rest of his life. I am telling you all this for a reason. When the story reaches 2012, and an old man stands up to suggest that the holy grail of theoretical physics may be permanently out of reach, you need to know exactly who is speaking, not an outsider, not a mystic, the man who unified the quantum theory of forces at 25, on a bus. A man whose entire career had been a demonstration that no calculation is too audacious, who designed spaceships meant to ride nuclear explosions, who imagined how civilizations might wrap entire stars in shells to harvest their light, who was accused many times of dreaming too big and never once of dreaming too small. When a man like that tells you something may be impossible, it is not timidity talking. He has done the sums. And there is one more thing you should know about him, the thing his colleagues mention first when they remember him. Dyson had a lifelong, almost mischievous suspicion of consensus. He called himself a rebel by conviction. He took contrarian positions cheerfully, sometimes to his cost, because he believed the health of science depends on somebody poking the places everyone else has agreed not to poke. For half a century, the consensus in fundamental physics had been that gravity must be quantized, that the graviton must exist, and that the only interesting question was which mathematical road, strings or loops or something else, would lead to it fastest. Thousands of careers were built inside that assumption. Almost nobody thought to ask the childlike question underneath it. Sure, but could you ever see one? So in 2012, invited to deliver a prestigious lecture, the Henri Poincaré Prize Lecture, at the International Congress on Mathematical Physics in Aalborg, Denmark, Dyson, then 88 years old, chose that question as his title. Is a graviton detectable? Not, does the graviton exist? Not, which theory of quantum gravity is correct? Something humbler and far more dangerous. Can any experiment, any instrument, any arrangement of matter, permitted by the laws of physics, ever register the absorption or emission of a single quantum of gravity? Because if the answer is no, a strange philosophical trapdoor opens beneath the entire enterprise. A particle that cannot be detected even in principle, he pointed out, is a particle whose existence is not really a scientific question anymore. If no possible observation could ever tell a universe with gravitons from a universe without them, then the century-long war over how to quantize gravity might be a war over words, fought on a battlefield that nature never built. He was not saying the graviton does not exist. He was asking whether the universe has left the question answerable, and he suspected, with evident enjoyment, that it might not have. Physics has been in this uncomfortable position before, and the precedent would have been in every listener's mind. At the end of the 1800s, the great physicist and philosopher Ernst Mach refused to believe in atoms, on the grounds that nobody had ever observed one, and perhaps nobody ever could. And he dismissed them, witheringly, as a metaphysical convenience. Have you ever seen one? He liked to ask. It took Einstein's analysis of pollen grains jittering in water, in that same miraculous year of 1905, to drag atoms across the line from useful fiction to established fact. The lesson cuts both ways, and Dyson knew it. Sometimes, the undetectable becomes detectable, and the skeptic ends up on the wrong side of history. But sometimes a question really is closed, and the honest thing is to say so. Which kind of question is the graviton? That is precisely what his lecture set out to decide. Picture the scene for a moment, because it is worth keeping. A conference hall full of the world's mathematical physicists, many of whom have spent their professional lives on quantum gravity in one form or another. At the lectern, a small, wiry Englishman in his 9th decade, formal and precise in the old style, with a habit of pausing before the important sentences as if giving you time to put your affairs in order. He is one of the last living links to the founding generation, a man who corresponded with Einstein's contemporaries, and he has come, with immaculate politeness, to tell the room that the door they have all been pushing on for 50 years may have no other side. There is no anger anywhere in the lecture. There is, instead, a kind of delight. Dyson thought the possible undetectability of the graviton was not a tragedy, but one of the most interesting facts he had ever uncovered. A joke the universe had been patiently waiting 80 years for someone to notice. His method was the opposite of hand-waving. He simply took the ways one could imagine catching a graviton, sorted them into categories, and worked each one to the bottom, with the plain quantitative honesty he had practiced since Bomber Command. Can you detect a single graviton by its gravitational effect on an instrument, the way we detect gravitational waves? Work it out. Can you produce gravitons on demand by collision, the way we produce the W, the Z, and the Higgs? Work it out. Can you find a natural source in the sky that showers us with gravitons, and then catch one, the way we catch particles from the sun? Work it out. Can you convert gravitons into something friendlier, light, for instance, and detect that? Work it out. 4 families of strategies. Every plausible route anyone had proposed fits into one of them, and over the next several parts of tonight's journey, we are going to walk each route exactly as he did, all the way to where it ends. And I will tell you the shape of what we will find, so you can listen without suspense, but with attention, the way one listens to slow music. Some of the routes end in absurdity, in machines the size of star systems and weights the length of geological ages, projects that are technically legal under the laws of physics, but comically beyond any civilization's reach. Those are the merciful endings. The other routes end in something much stranger. They end in walls that the laws of physics build themselves, actively, in front of the measurement. Follow one route to its conclusion, and a black hole forms, precisely where your instrument needed to be, and swallows the answer. Follow another, and the vacuum of empty space itself gives way before the signal can arrive. 2 different roads, 2 completely different corners of physics, and at the end of each one, the universe performs what looks unmistakably like an act of concealment. It was Dyson's genius to notice the pattern, and it is the pattern, more than any single wall, that lodges under the skin, as if the universe were keeping its own foundations out of sight. He died in February of 2020, at 96, with his question still open, and with the first serious attempts to answer it just beginning to stir in laboratories he would have loved to visit. We will get to those, but first, we owe the old man the walk he mapped. The first route is the most natural one, the one that starts from humanity's greatest measuring instrument, a machine so sensitive it can feel 2 black holes touching in another galaxy. If anything we own could feel a single graviton, surely it would be that. So let's go to Louisiana, in the dark, and stand next to the most delicate ruler ever built. Route 1 begins with the most natural idea in the world. Gravity pulls on things. A graviton is a piece of gravity. So build an instrument sensitive enough to feel the pull of a single piece. To understand why Dyson took this route seriously enough to demolish it carefully, you have to understand the machine that made it thinkable, because humanity has, in fact, built an instrument that feels gravity's ripples. It is called LIGO, the Laser Interferometer Gravitational Wave Observatory, and it is, by a comfortable margin, the most sensitive measuring device our species has ever constructed. Come and see it. It is night in the pine flats of Livingston, Louisiana. In front of you, low and pale under the stars, a concrete tunnel runs away from you in a perfectly straight line until perspective swallows it. It is 4 kilometers long. Somewhere far to your left, its twin runs exactly perpendicular, the 2 arms meeting at a corner station, glowing with quiet control room light. Inside each arm is a steel vacuum pipe, and inside that pipe is an emptiness more perfect than the space between the planets, because air itself would ruin what happens here. Down the center of each arm runs a single, unbroken thread of laser light. At the far ends hang mirrors, 40 kilograms of fused glass polished so finely that if one were scaled up to the size of the Earth, its tallest mountain would rise a few centimeters. They hang from glass fibers, isolated from the trembling ground by cascades of pendulums, so that they float, as nearly as anything on this noisy planet can, in free fall. The laser light bounces between the mirrors roughly 300 times, folding a 4-kilometer arm into more than 1,000 kilometers of measured path, and then the light from the two arms is recombined and compared. If the two arms are precisely the same length, the light waves cancel in a particular way, and a detector sees darkness. If anything changes one arm's length relative to the other, by any amount, the cancellation slips, and light leaks through. You are standing inside a question that is being asked continuously, thousands of times per second, in a perfect whisper. Has the length of space itself just changed? And sometimes, the answer is yes. Remember the kneading motion we filed away earlier, the signature of a spin-2 ripple, space stretched in one direction and squeezed in the perpendicular one. Two arms at right angles are a trap built precisely for that shape. On the 14th of September 2015, at a few minutes before 11 in the morning Universal Time, both LIGO detectors in Louisiana and in Washington State twitched in the same pattern within 7,000ths of a second of each other. The pattern was a rising chirp, a wobble that sped up and strengthened and then rang down into silence, all within a fifth of a second. It was the sound, translated into geometry, of two black holes, 36 and 29 times the mass of our Sun, ending a spiral dance that had lasted perhaps billions of years in a galaxy 1.3 billion light-years away. In the final fraction of a second, 3 entire suns' worth of mass ceased to exist as matter and became pure ripple, and for that instant, the collision radiated more power than the combined light of every star in the observable universe. That is what it took, that apocalypse, to move LIGO's mirrors. And how far did they move? The wave changed the 4-kilometer arm lengths by about 1,000th of the width of a proton. Not 1,000th of an atom. An atom would be a continent here. 1,000th of the width of a single proton, the tiny kernel at an atom's heart. Measured, cleanly, by human beings, with a laser and some mirrors and 40 years of stubbornness. To say the same thing another way, LIGO's precision is equivalent to measuring the distance from Earth to the nearest star beyond the Sun, 40 trillion kilometers, and noticing when it changes by the width of a human hair. And here is a detail that makes the loudness of the source and the faintness of the signal sit strangely together in the mind. By the time that wave reached Earth, the energy it carried across each square meter was comparable to the light of the full moon falling on your upturned face. Moonlight, roughly speaking, in gravitational form, washed over the whole planet, and the whole planet stretched and squeezed by 1,000th of a proton in response, and no living thing anywhere on Earth felt a thing. That is how stiff spacetime is, and how weak gravity's grip on matter is, both at once. The physicists who conceived and led that instrument received the Nobel Prize, and the detection opened an entirely new sense with which our species now listens to the universe. Hundreds of these collisions have been catalogued since. So the question almost asks itself, if we can feel two black holes merging in another galaxy, how much better would the instrument have to get before it could feel one graviton? This is where Dyson sat down with his pencil, and this is where the story begins its slow turn into the uncanny. Start with the wave LIGO caught. If gravity is quantum, that gravitational wave was not a smooth ripple. It was a chorus, a coherent flood of gravitons, all oscillating together, exactly as a laser beam is a coherent flood of photons. Count the members of the chorus, and you get a number that should raise the hair on your arms, gently, because you have met it before. A gravitational wave at LIGO's detection threshold contains at least 10 to the 36th power gravitons, a 1 followed by 36 zeros, the same absurd number. It appeared first as the ratio of gravity's weakness, and here it is again, in a different costume, counting the voices in the choir that our finest instrument can only just barely hear as a single blended hum. I told you it would come back, and I make no claim yet about what the recurrence means. Just notice it, file it, and keep drifting with me. To hear one voice, instead of 10 to the 36, you need, naively, a detector 10 to the 36 times more sensitive. Dyson asked what that means physically, and the answer turns out to be beautifully independent of the details. To register the passage of a single graviton by its effect on separated mirrors, your instrument must resolve a change in distance of about 1 Planck length. We met Max Planck's natural units earlier, and here is the length among them, the distance you get by combining gravity, quantum theory, and the speed of light into a single scale. It is 10 to the minus 35 meters, give or take. 16 billionths of a billionth of a billionth of a billionth of a meter. 20 powers of 10 smaller than a proton. If you inflated a single proton until it was as large as the entire observable universe, 93 billion light-years across, the Planck length inside it would inflate to roughly the size of the Earth. That is the precision the measurement demands. Not as a stretch goal, as the entry fee. And now the trap springs, quietly, one clause at a time. How do you measure the distance between two mirrors with extreme precision? You bounce light between them. But light carries momentum, and every bounce kicks the mirrors, and Werner Heisenberg's uncertainty principle makes the trade-off unbreakable. The more precisely you wish to know a position, the shorter the wavelength of light you must use. And the shorter the wavelength, the harder the kick. And the harder the kick, the faster your mirrors drift out of the very position you were trying to pin down. There are two honest defenses, and only two. Make the mirrors heavier, so the kicks disturb them less, and bring them closer together, so the measurement takes less time and the drift has less opportunity to accumulate. Heavier and closer. Heavier and closer. Follow the logic toward Planck length precision, and the requirements compound, the mirrors growing more and more massive, the gap between them shrinking and shrinking, until you cross a line that has nothing to do with engineering. The mass required, packed within the separation required, exceeds the density at which general relativity permits an object to exist. The mirror's combined mass falls within its own Schwarzschild radius. Your apparatus becomes a black hole. Stay with that for a moment, in the dark, because it deserves your full attention. This is not the failure of a budget or a technology. Nothing was built poorly. The failure is written into the laws themselves. Quantum mechanics, through the uncertainty principle, demands ever heavier mirrors, ever closer together. General relativity, through the physics of black holes, forbids exactly that combination. The two theories, the very pair whose reconciliation the graviton would embody, jointly conspire to destroy the instrument at precisely the sensitivity where it would have succeeded. An event horizon forms around your measurement, and an event horizon is, by definition, a surface from which no information returns. The answer does not merely elude you, it is sealed, by the geometry of spacetime, into a region from which answers do not come back. Dyson checked the obvious escape, bolting the mirrors in place rather than letting them float, and the argument reforms in different clothing and delivers the same verdict. Any measurement of any distance, by any means, at Planck length precision, summons a black hole. The scale at which spacetime would show its grain is guarded, it turns out, by spacetime's own most absolute lock. And there is a haunting historical footnote here. In the 1930s, the young Soviet physicist Matvei Bronstein ran an early version of this same analysis and saw the same wall rising, decades before anyone was ready to listen. The wall has been standing in the mathematics, patiently, for 90 years. So route 1 ends, and note carefully how it ends. Not in difficulty, in principle. The universe does not say, come back with better mirrors. The universe says no, and enforces the refusal with a black hole. One route down, and already the pattern Dyson noticed is glinting at us from the shadows. But perhaps we were too gentle. Perhaps tiptoeing around the graviton with mirrors was always the wrong posture. When physicists wanted the Higgs boson, they did not wait to feel one drifting past. They smashed matter together with such violence that the field itself was forced to cough its particle up. There is a second route, the brute force route, and walking it will require us to build, in imagination, the most absurd machine ever seriously described in a physics lecture. Bring a coat. It is 3 light years long. If you cannot sneak up on a particle, you can try to manufacture it. This is the strategy that built modern physics, and it deserves a fair hearing, because it has never failed before. The recipe is always the same. Energy can become matter. That is the working meaning of Einstein's most famous equation. So if you want a particle the universe is not currently offering you, you collide other particles with enough combined energy to pay for the one you want. And quantum field theory hands it over. Want a W boson? Collide protons at sufficient energy, and the weak field yields its messenger. Want a Higgs? That purchase cost more, which is why it took until 2012 and required the Large Hadron Collider, the 27-kilometer ring beneath the French-Swiss countryside, where protons are whipped to within a whisper of the speed of light and slammed together head-on, hundreds of millions of times each second, inside detectors the size of cathedral naves. The Higgs boson duly appeared, right where half a century of theory had pointed. Production on demand. The factory method. Route 2 asks the obvious question: why not a graviton factory? There is one immediate difference from the Higgs. The graviton is massless, so we are not saving up to pay for its mass. But the coupling problem we met earlier now returns wearing its work clothes. The probability of a collision producing a graviton is controlled by gravity's coupling strength at that collision energy, and at any energy a human machine has ever reached, that probability is ruinously, insultingly small. The coupling grows as the energy climbs, and it reaches respectability, parity with the other forces, only at the threshold we have already named, the Planck energy, 2 billion joules in a single pair of colliding particles, the freight train compressed into 2 protons. The Large Hadron Collider reaches about 2 millionths of a joule per collision, and before we scale beyond it, pause to honor how strange even that number is. 2 millionths of a joule is roughly the kinetic energy of a flying mosquito. The most powerful machine our species has ever assembled, decades in design, tens of billions in cost, 100 nations worth of physicists, achieves, per collision, the energy of a mosquito in flight. The miracle of the LHC is not the total energy, it is the concentration, that mosquito's worth, loaded into a volume a millionth of a billionth the width of the insect. But the Planck energy demands the freight train in that same tiny volume, and the gap between the mosquito and the train is a factor of a million billion, 15 zeros of shortfall. And in case you are wondering whether nature's own accelerators can close the gap, the universe has been running that experiment over our heads all along. The most energetic cosmic ray ever recorded, a single atomic nucleus that struck the atmosphere over Utah in 1991, carried about 50 joules, the energy of a well-thrown baseball packed into one nucleus. So shocking that physicists nicknamed it the "oh my god" particle. It remains the most violent single particle humanity has ever registered, accelerated by some monstrous astrophysical engine we still have not identified, and it falls short of the Planck energy by a factor of tens of millions. Even the universe's own most furious slingshots, whatever they are, do not obviously reach the graviton's checkout counter. So let's do what physicists do on the blackboard, and simply scale the machine up, because the scaling law is clean. In a ring collider, for a fixed strength of bending magnets, the achievable energy grows in direct proportion to the size of the ring. Double the circumference, double the energy. The LHC's magnets are already among the strongest ever mass-produced, superconducting coils cooled below the temperature of deep space. So let's grant ourselves LHC-grade magnets and simply ask how big the ring must be to hold particles carrying the Planck energy. Multiply the 27 kilometers by the missing factor, and the answer comes back serenely ridiculous. The ring would be about 3 light-years across. Let's actually build it, you and I, since we are lying comfortably in the dark with time to spare. Begin at the LHC's scale, a ring you could cycle around in an afternoon, buried under farmland and vineyards. Now inflate it. The ring swells past the orbit of the moon, 1 1/3 light seconds out, and keeps growing. It swallows the orbits of Venus and Mars, and the sun itself is now inside the machine, 8 light minutes from the beamline. Keep going. The ring passes the great slow circles of Jupiter and Saturn, out past Neptune, 4 light hours from the center, and the entire solar system, every planet, every moon, every scrap of humanity's history, and every place a spacecraft of ours has ever touched, is now a small bright smudge far inside the accelerator complex. And the ring keeps growing. Voyager 1, the farthest object human beings have ever flung, almost 50 years out, less than 1 light day from home, has not even reached the service corridor. The ring grows past the comets of the Oort cloud, through a light year of interstellar dark, then 2, and finally, 3 light years out, it closes on itself. The nearest star to our Sun, Proxima Centauri, lies just beyond, at 4 1/4 light years. Our collider's far wall stands most of the way to another solar system. A beam injected at one point would need 3 years, at the speed of light, simply to go around once. This is the machine that the numbers demand. Dyson, who had spent a lifetime around grand engineering dreams and had authored a few of his own, gave it a name in the spirit it deserved. Where physics has its very large array and its extremely large telescope, this would be the stupidly large collider. And here is the remarkable thing, the reason this part of the story is comedy rather than tragedy. Nothing in the laws of physics forbids it. Unlike the mirror trap, which ended in an event horizon and a slammed door, the stupidly large collider is merely absurd. It violates budgets, lifespans, engineering, and good taste, but not physics. A civilization unimaginably beyond ours, with a few thousand years to spare and a solar system's worth of raw material, could in principle build it, run it, and mass-produce gravitons. Route 2, unlike Route 1, stays technically open. Dyson noted the distinction with care because it matters for the final verdict. Some walls are laws, others are just very, very high. But now comes the twist that turns Route 2's comedy bleak, and it is a twist most tellings of this story miss. Suppose the machine is built, suppose the collisions are running, and gravitons are streaming out of the interaction points. How do you know? How do you see them? With the Higgs, the answer was decay. The Higgs boson lives for 1/10000000th of a trillionth of a second, and then shatters into ordinary particles, photons, electrons, muons, things our detectors catch routinely, and we reconstruct the parent from the debris, the way you might deduce a vase from its shards. The graviton offers no such courtesy. A massless particle has nothing lighter to decay into. Gravitons are perfectly stable. They do not shatter, do not announce themselves, do not leave debris. A graviton born in your collider simply departs, at the speed of light, forever. The factory produces its product and ships it, unlabeled, into the cosmos. Your only hope is to catch one directly, to build some slab of material in which a passing graviton will occasionally interact, deposit its energy, and register a click, the way the photoelectric effect catches photons in metal. And with that, we are thrown back onto the question of how eagerly matter receives a graviton, which physicists express through a quantity called a cross-section. Think of it as the size of the target a particle presents to the world. When a photon meets an atom, the atom presents an ample target, and the photon is absorbed within, say, the thickness of a sheet of paper or the surface of your skin. Ask the same question for a graviton meeting an electron, and the mathematics returns a target area proportional to the square of the Planck length. In ordinary units, that is about 10 to the minus 70 square meters. The atom's target, for comparison, is around 10 to the minus 20. The graviton's is 50 orders of magnitude smaller. There is no honest analogy for 50 orders of magnitude, but let's at least gesture at it. The step from a single atom up to the entire observable universe is about 37 orders of magnitude in size. 50 orders is that entire ladder, climbed top to bottom, with 13 more rungs to spare. To a graviton, an electron is not a small target. It is a target smaller than smallness itself, a bullseye the size of a mathematical point wearing a coat. So route 2 ends in a place stranger than failure. We could, in principle, build the factory. 3 light years of magnets, 3 years per lap, a machine wrapped around the void between stars, and it would work. It would make gravitons. And then they would leave, invisibly, through detector walls that might as well be fog, and the machine would stand there, the greatest construction in the history of matter, having proved nothing, a monument to the difference between making and seeing. The factory is legal. The camera is what the universe declines to sell us. Unless, of course, we stop trying to make gravitons at all, and notice that something has been making them for us, continuously, in numbers beyond counting, for 4.5 billion years, at a comfortable distance of 150 million kilometers from your bed. The sun, it turns out, is a graviton lamp, and several of its gravitons have passed through your body since I began this sentence. We are near the middle of the night, so let's pause for a breath and stack the pieces we have gathered, because they are about to combine into the strangest part of the whole story. We learned that every force of nature except gravity has shown us its messenger particle, and that gravity's messenger, the graviton, has been named and characterized but never seen. We learned that if it exists, space-time itself is made of it, which makes it not just another particle, but the grain of the stage. We learned that gravity is weaker than the other forces by a factor of 10 to the 36, which makes its messenger the faintest whisper in nature, and we learned that a gravitational wave, loud enough for our best instrument to hear, is a chorus of at least 10 to the 36 of them, the same absurd number twice. And we walked 2 of Dyson's 4 routes to catching one. The mirror route died in principle, sealed behind an event horizon of its own making. The collider route survives in principle and dies in practice. 3 light years of magnets shipping invisible products to nowhere. 2 routes remain. Both begin with the same realization. If making gravitons is the problem, stop making them. Find where the universe already makes them, and stand in the stream. And the universe does make them. This is worth saying slowly, because everything so far has made the graviton sound like a creature of impossible machines and alien energies. And yet, if gravity is quantum, gravitons are among the most ordinary things in existence. They are being manufactured right now, in astronomical numbers, by the most familiar object in your sky. Steven Weinberg, the same physicist whose theorem told us the graviton had no choice about its own properties, sat down and calculated what a star does in quantum gravitational terms. Far down in the sun's core, 150 million kilometers from your bedroom, matter is crushed to densities and temperatures beyond anything on Earth, 15 million degrees, and particles collide there, constantly, violently, everywhere. Every collision that jostles a charged particle shakes its gravitational field along with it, and a shaken quantum field occasionally sheds a quantum. Once in a very great while, by the miserly coupling we now understand, a collision in the solar core emits a graviton. The odds per collision are hopeless, but the sun is not a laboratory running one collision at a time. The sun is 10 to the 57th particles colliding without rest, and hopeless odds, multiplied by an inconceivable number of attempts, becomes a steady industrial output. Weinberg's arithmetic put the sun's production, in the useful energy range, at roughly 10 to the 24 gravitons per second. A trillion gravitons, every second, streaming outward in all directions, and it has been running at this rate, without interruption, for 4.5 billion years. Divide that output across the great sphere of space at the Earth's distance, and the stream becomes intimate. About 4 gravitons pass through every square meter of the Earth, every second, which means they pass through you. Lie still, and consider what is, if gravity is quantum, literally happening in your bedroom tonight. You are lying in a thin, perpetual drizzle of gravitons. A few pass through the area of your body every second. They passed through you at this rate on the day you were born, and every night of your childhood, through every ceiling you have ever slept beneath. They are passing through you now, in the dark, as you listen to my voice, quanta of the field that holds you to your mattress, sleeting through the room in silence. Follow one. It is born in this second, in the crush at the center of the sun, in a collision between two particles that will never do anything else of note for 1 billion years. A photon born beside it faces a terrible journey, absorbed and re-emitted so many times in the dense solar interior that its light can take 100,000 years to stagger to the surface. Our graviton does not stagger. To a particle that ignores matter, the sun is glass. It crosses 700,000 kilometers of star, the plasma, the roiling convection, the boiling surface, in about 2 seconds, unbent and untouched, and then it is in open space, falling outward at the speed of light. 8 minutes and 20 seconds of quiet vacuum. Then, ahead, a small blue world. It meets the atmosphere and does not notice. It passes through the roof of your home without an event, through the ceiling, through the blanket, and then through you, through the water and carbon of your chest, between the atoms and through them, through your heart as it beats once, out through your back, through the mattress, the floor, the foundations, and then into the rock. And here is where the story becomes almost unbearable in its gentleness. It passes through the entire Earth, 13,000 kilometers of iron and stone, the mantle, the molten core, all of it, as if the planet were a soap bubble, and emerges from the far side of the world, over an ocean lit by different stars, and continues, outward, forever. Nothing touched it. Nothing ever will. There is something worth holding on to in that image before we go on, something almost consoling. Physics is often accused of describing worlds too remote to matter, and quantum gravity most of all, a subject of blackboards and impossible machines. But notice what the theory just did. It reached into your bedroom. The claim that gravity is quantum is not, in the end, a claim about distant mathematics. It is the claim that a fine, real, countable rain has been falling through your body every second of your life and through every bedroom of every person who has ever slept. A rain nobody has ever felt because feeling it is all but forbidden. Whether or not anyone ever catches a graviton, this is what the equations assert is happening, tonight, in the most ordinary darkness you know. If that is true, the deepest layer of reality has been brushing past you, gently and without exception, your whole life. Because here is Weinberg's second number, the one that turns the drizzle into a parable. Take all the solar gravitons passing through the whole Earth, every second, that whole silent weather. Ask how often even one of them actually interacts with even one particle of terrestrial matter, anywhere in the planet's entire volume. The answer is about once every billion years. Read that at the scale it deserves. The Earth, 6 trillion kilograms of matter, the densest wall we can offer, functioning as a graviton detector, registers roughly 1 click per billion years. In the entire history of this planet, 4.5 billion years of uninterrupted bombardment, the Earth has stopped perhaps 4 or 5 of the Sun's gravitons. Your body, over an entire human lifetime, will almost certainly stop none. The odds that any graviton has ever interacted with any atom of any human being in the whole history of our species round comfortably to 0. You have been transparent to the deepest layer of reality since the day you were born, and it has been transparent to you. The intimacy runs in both directions, and so does the untouchability. They are always passing through you, and they will never once touch you. Still, an astronomer hears 1 click per billion years and starts optimizing, because that is what astronomers do. The Sun is a mediocre graviton lamp, as stars go. Graviton production loves density and temperature, so the better lamps are the corpses of stars. Robert Gould worked out the figures. A hot white dwarf, a dead star compressed to the size of the Earth, outshines the Sun in gravitons by a factor of about 100. A neutron star, matter crushed to a city-sized sphere so dense a teaspoon of it outweighs a mountain range, does better still, up to 100,000 times the Sun's output. So relocate the experiment, build a detector with the mass of a planet or a star, and park it in close orbit around a neutron star, and the arithmetic finally begins to soften. 1 graviton event per billion years becomes, with enough audacity, an event every few years, perhaps every few months. A detection within a human lifetime, in the mathematics at least, becomes possible. The engineering is a fantasy of the same genus as the stupidly large collider, dismantled planets, star-lifted material, structures beyond any physics we could fund. But Dyson's question was never about funding. It was about principle, and in principle, Route 3 is still breathing. Then the fog rolls in, because a neutron star does not radiate gravitons into a silent sky. It radiates everything, and above all, it radiates neutrinos, and neutrinos are the cruelest possible companion for this particular search. You may know neutrinos as the famous ghost particles, the ones that slip through planets as if they were not there. 65 billion of them, from the Sun alone, are passing through every square centimeter of your skin, every second, and essentially none will interact with you in your lifetime. Physicists had to bury tanks of 600 tons of fluid in mines to catch a handful per week. Raymond Davis waited in the dark of a South Dakota gold mine for years, catching roughly 1 solar neutrino every other day, and won a Nobel Prize for it. The neutrino spent 26 years as physics' own undetectable particle, promised by theory in 1930, and finally caught in 1956. By every human standard, the neutrino is elusiveness itself. And next to the graviton, the neutrino is a party animal, a socialite, practically luminous. For every graviton your detector near the neutron star might absorb, it will be struck by about 10 to the 34 neutrinos. Notice the costume change, but recognize the actor. 10 to the 34, next of kin to our recurring 10 to the 36. The number changed by a whisper, the absurdity did not. Somewhere in that flood of 10,000 billion neutrino events hides 1 click that means everything, and no shield known to physics stops neutrinos while passing gravitons, because anything dense enough to block neutrinos is still glass to gravity's messenger. The signal is not too faint. It is buried beneath the loudest quiet noise in the universe. So Route 3 ends not with a wall but with a fog, a signal drowned by a factor written with 34 zeros. And Dyson had 1 route left, the cleverest of the 4, a scheme that does not ask matter to catch a graviton at all. It asks light to do it, using a trick of resonance discovered by a Soviet physicist in 1962. A trick that, on paper, converts gravitons into ordinary photons, the one particle we catch, better than any other. It is the most promising route of the 4, which is exactly why what the vacuum does to it is the strangest thing in this entire story. The 4th route begins with a piece of physics so elegant that, the first time you meet it, You feel certain it must be the answer. It was discovered in 1962 by a Soviet physicist named Mikhail Gertzenstein, working in the same remarkable Moscow scientific culture that gave the graviton its name, and it concerns a secret kinship between light and gravity. Here is the kinship. Electromagnetic waves and gravitational waves are profoundly different things. A ripple of fields on spacetime and a ripple of spacetime itself. But they share one crucial property. Both travel at exactly the speed of light. And in physics, two waves that travel at the same speed can do something special. They can run alongside each other, crest match to crest, mile after mile, without ever drifting apart. And matched waves can resonate, feeding energy from one to the other, the way a singer, holding precisely the right note, can feed energy into a wine glass until it hums. Gertzenstein showed that a strong magnetic field acts as the coupling between them, the shared medium through which the two kinds of wave can trade energy. Send a gravitational wave through a region threaded by an intense magnetic field, and as it travels, some of its energy converts into an electromagnetic wave of the same frequency, riding along in step. In quantum language, the statement is sharper and more startling. Inside a strong magnetic field, a graviton can transform into a photon, and a photon into a graviton. You can see why this looks like the master key. Every route so far has died on the same reef. The fact that matter will not talk to gravitons. 10 to the minus 70 square meters of conversational interest. But this scheme never asks matter to talk to a graviton. It asks a magnetic field to persuade the graviton to become something else, and photons we can catch in our sleep. Photons are the one particle humanity detects, with century-old confidence, one at a time, click by click. So the detector designs itself. Build a long tube, pump it to a hard vacuum, thread it with the strongest magnetic field you can sustain, and point it at a source of gravitons, the sun, a white dwarf, a neutron star. Inside the tube, once in a while, an incoming graviton flickers into a photon. At the far end, a photon counter waits in the dark. Every click is a caught graviton, laundered into a currency we can bank. No Planck-length precision, no 3-light-year ring, no planet-sized slab, just a tube, a field, and patience. On paper, it is the most beautiful graviton detector ever conceived. Now watch what the universe does to it. The conversion is efficient enough to matter only if the magnetic field is monstrously strong, and the required strength approaches a threshold with its own name and its own dark reputation, the Schwinger limit, around 4 billion Tesla. For comparison, the strongest continuous magnetic fields human laboratories produce are around 45 Tesla. A hospital scanner manages about 4 billion Tesla is the regime where the electromagnetic field becomes so intense that it starts to tear at the structure of nothingness itself. Because in quantum field theory, the vacuum is not empty. It seethes, everywhere and always, with virtual particles, pairs of electrons and anti-electrons that flash into being and annihilate faster than anything can notice them, a froth of almost existence underlying every cubic centimeter of space, including the space inside your bedroom and the space inside your bones. Under ordinary conditions, the froth stays virtual, borrowing energy and repaying it too quickly to leave a trace. But bathe it in a field near the Schwinger limit, and the loans stop being repaid. The field rips the virtual pairs apart before they can recombine, promoting them into real electrons and real anti-electrons. Empty space begins, quite literally, to spark. The vacuum breaks. And a broken vacuum is exactly the wrong place to run a resonance. Remember, the whole trick depends on the light wave and the gravitational wave staying perfectly in step over the length of the tube. But space now filled with conjured electron pairs is no longer a clean vacuum for light. It has become a medium, and light moving through a medium slows, scatters, loses its phase, falls out of step with the gravitational wave it was supposed to shadow. The singer's note goes flat, the wineglass stops humming, and the conversion shuts down. Strengthen the field to improve the coupling, and you thicken the fog that destroys the coherence. The scheme does not fail at the edges, it fails at the center, by the same logic as the mirrors. The mirror trap was quantum mechanics and general relativity teaming up to hide the answer behind an event horizon. The Gertzenstein trap is quantum field theory reaching into its own vacuum and pulling out a screen of static, precisely at the field strength where the trick would begin to work. The two most beautiful detection schemes anyone ever devised, and each is dismantled at the decisive moment by the very physics it was built to reveal. So let's stand still and take the honest tally, exactly as Dyson took it at the end of his lecture. 4 routes: the mirror route, forbidden in principle, sealed by a black hole; the collider route, permitted in principle, absurd in practice, and blind, even in success, since the factory ships products no camera can photograph; the stellar route, permitted in principle, demanding planet-sized instruments beside dead stars, and delivering, even then, a signal buried under 10 to the 34 neutrinos; the conversion route, forbidden in principle, shut down by the breakdown of the vacuum. 2 doors locked by the laws of physics themselves, 2 doors technically ajar, but opening onto corridors of such absurdity, machines the size of star systems, weights the length of geological ages, that no civilization recognizable as our descendants would ever walk them. That is the whole map. Every scheme anyone had proposed, in 80 years of thinking about this particle, lands somewhere on it. And now, at the bottom of the night, let yourself feel the pattern, because it is the pattern that Dyson wanted the world to see, the pattern I promised in Louisiana. Each individual wall has a technical explanation, blameless and local. But step back, and the walls compose. The uncertainty principle summons black holes at precisely the sensitivity that would reveal the grain of space-time. The quantum vacuum sparks into static at precisely the field strength that would convert gravity into light. Weakness buries the signal, neutrinos flood the sight, and the same absurd number, 10 to the 30-something, stamps itself on every failure like a signature at the bottom of every page, as if the universe were keeping its own foundations out of sight. When I first said those words, hours ago, they were a poetic suspicion. They are not poetry anymore. They are a summary of the data. Dyson, being Dyson, followed the pattern to the most heretical conclusion available. Perhaps, he suggested, the concealment is the message. Perhaps single gravitons are unobservable in every possible universe consistent with our laws, and if so, perhaps the graviton is not physics at all, and the two great theories are under no obligation to merge. Maybe space-time really is smooth and classical to the bottom, a continuous stage, while only the actors upon it are quantum, and the century-long search for quantum gravity has been a search for a bridge between two shores that were never meant to touch. He offered it lightly, as a possibility rather than a creed, but he meant the challenge underneath it seriously. Show me the observation, any observation, that certifies gravity is quantum. In 2012, nobody could. Tonight, as you lie there, still nobody can. It remains a fact, quietly scandalous, that the most confident structural belief in fundamental physics, the quantization of gravity, is supported by every theoretical instinct we have, and by not one single measurement. Most physicists, it is fair to say, believe Dyson's escape hatch leads nowhere, and their reasons are strong. A classical gravitational field, attached to quantum matter, is a creature with consistency problems. Matter can be placed in superposition, genuinely in two configurations at once, and experiments do this routinely with objects as large as complex molecules. What, then, does the classical gravity of a superposed mass point at? An experiment as far back as 1981, using a torsion balance, watching masses whose positions depended on quantum events, already ruled out the crudest version of the compromise. And a newer generation of tabletop proposals aims to test the question directly by checking whether gravity alone can entangle two tiny masses, something no classical field could ever do. But notice what all of this is: arguments, models, proposals. The counter case to Dyson is made of theory. His challenge was made of experiments, and it stands. That is where the story stood for a decade. A locked map, a heretic's smile, and a silence where the evidence should be. If the night ended here, it would end as a beautiful defeat. It does not end here, because while the theorists argued about the map, a small group of physicists went back to the oldest, most discredited instrument in the whole history of gravitational science. A machine physics had buried half a century ago with something close to embarrassment, and realized that with 21st century quantum eyes, it might do what LIGO never could. The next part of our story is about a metal cylinder, colder than the space between galaxies, waiting for a single click. Before LIGO, before the lasers and the 4-kilometer arms, gravitational wave hunting began with a man and a metal cylinder, and it began in heartbreak. His name was Joseph Weber, and in the 1960s, when almost nobody believed gravitational waves could ever be detected, he decided to try anyway. His instrument was almost defiantly simple: a solid aluminum cylinder, about 1.5 tons, suspended in vacuum, isolated as well as the era allowed. The idea was that a passing gravitational wave, that kneading of space we have followed all night, would set the bar faintly ringing at its natural frequency, like a struck bell, and sensors wrapped around its waist would pick up the hum. Physicists called them Weber bars. In 1969, Weber announced that his bars, one in Maryland and one near Chicago, were ringing in coincidence, and for a heady year or two, he was the most famous experimental physicist in the world, the man who had heard Spacetime. And then the story collapsed. Other groups built bars, better bars, colder bars, and heard nothing. The claimed signals implied a universe absurdly loud in gravitational waves, thousands of events that LIGO, decades later, would demonstrably not see. By the mid-1970s, the community's verdict was in. Weber had been hearing noise, and his refusal to accept it clouded the end of his career. He kept running his bars, increasingly alone, until his death in the year 2000. The field he founded moved on to lasers and interferometers, and the Weber bar was shelved as a cautionary tale, the wrong instrument, from the wrong era, remembered mostly for a mistake. Cryogenic descendants of his bars ran quietly for years, cooled to 1/10 of a degree above absolute zero, and never caught a confirmed wave. When the Nobel Prize was awarded for gravitational waves in 2017, it went to the interferometer people. History had filed the resonant bar under noble failures. Hold that verdict in your mind, and now watch it come undone. In 2024, in the journal Nature Communications, 4 physicists, Germain Tobar, Srinath Manikandan, Thomas Beitel, and Igor Pikovsky, published a paper with a title that, to anyone versed in Dyson's lecture, read as a straight-faced provocation: detecting single gravitons with quantum sensing. Their proposal, when you unwrap it, is a Weber bar, a solid metal cylinder, suspended, waiting to ring. But it is a Weber bar reimagined through everything physics has learned in 60 years, and the reimagining attacks the exact wall where every previous route died. It went on to become the journal's most read physics paper of the year, some 34,000 downloads, which tells you something about how starved this field has been, for a century, for any experimental handle at all. Here is the insight, and it is worth taking slowly, because it is the first genuinely new move in this game in decades. Every catching scheme so far has asked a small quantum object, an electron, an atom, to absorb a graviton, and the smallness is the death sentence, 10 to the minus 70 square meters of target. But quantum mechanics has no rule that says a quantum object must be small. Cool a metal cylinder profoundly enough, close enough to absolute zero, and something wonderful happens to it. Its trillions of atoms stop behaving like a crowd and begin behaving like a single instrument. The collective vibrations of the whole bar, its ringing modes, become quantum states, with energy levels as discrete as the rungs of an atom's. The bar can no longer ring just any amount. It rings in exact, indivisible steps, and each step, each single quantum of collective vibration, is called a phonon, a particle of sound. A phonon in a 10-ton bar is a strange and beautiful thing. It is a quantum excitation, as genuinely quantum as an electron's jump, but its host is a macroscopic object you could walk around and lay your hand on. It is, in effect, a quantum particle the size of a truck, and a quantum target the size of a truck presents a cross-section for graviton absorption enormously larger than any electrons. The wall of 10 to the minus 70 was never a law about gravitons. It was a law about asking tiny things to do the catching, make the catcher's quantum big, and the odds climb from unthinkable to merely heroic. So the design assembles itself, and its numbers have the crisp specificity of something meant to be built rather than dreamed. Choose your bar to ring in tune with a known cosmic source. For the waves from merging neutron stars, the paper suggests a beryllium cylinder of about 15 kilograms, a thing you could carry with a colleague. For the deeper note of colliding black holes, near that piano's middle register of 175 cycles per second, a niobium cylinder of about 10 tons. When a gravitational wave of the matching frequency washes over the bar, there is now a small but honest probability, no longer a cosmic joke, that the bar absorbs exactly one graviton from the flood and hops up exactly one phonon step. One quantum of gravity, traded for one quantum of sound. The authors call the process gravito-phononic absorption, and you should hear in that name exactly what they intend you to hear. It is the photoelectric effect, staged again after 120 years, with gravity cast in the role of light, and a singing cylinder in the role of the metal plate. Einstein's 1905 experiment, rebuilt for the force he geometrized 10 years later. The price of admission is cold, and the cold is fearsome. For the bar's quantum steps to stand out, it must sit near its vibrational ground state, which for these frequencies means a temperature around 1,000th of a degree above absolute zero. 1 millikelvin, the space between galaxies, warmed by the afterglow of the Big Bang, sits at 2.7 degrees, nearly 3,000 times hotter. The bar must be colder than the void, colder than anywhere nature has been since nature began, and it must be that cold, while weighing 10 tons. Laboratories routinely park small chips at such temperatures. The great cryogenic bars of the 1990s reached about 1/10 of a degree at the ton scale. The final factor of 100 is brutally hard, and it is engineering, not law. Nothing in physics forbids a millikelvin cylinder, and the readout must perform a feat with a paradoxical name, quantum non-demolition measurement, watching the bar continuously for a 1 phonon jump without the act of watching kicking phonons into it. A discipline of looking without touching that laboratories have spent 2 decades learning on small superconducting circuits where single phonon jumps are now resolved as a matter of course. Everything here is hard the way LEGO was hard for 40 years. Nothing here is a black hole. But the finest move in the paper is not the bar. It is the alibi. Because a millikelvin cylinder will still click for 100 wrong reasons, a cosmic ray, a stray vibration, a thermal flicker that beat the odds, a twitch of the readout itself, and no amount of shielding brings the false clicks to zero. A single click, alone, means nothing, and the authors know it, so they do not listen alone. They listen alongside LIGO. Remember what a LIGO detection is, in quantum language. It is an announcement that a flood of 10 to the 36 gravitons of a known frequency from a known cataclysm is passing through the Earth right now. The bar cannot hear that flood as a flood. It is tuned to trade in single quanta. But if the bar jumps one phonon step at the very moment LIGO announces the flood, at the very frequency the bar was tuned for, then the coincidence transforms the meaning of the click. Noise does not schedule itself to the millisecond alongside a black hole merger a billion light-years away. Run the bar for months. Count the background clicks honestly, and when the one click lands inside the narrow window of a confirmed gravitational wave, the arithmetic of coincidence does the rest. If gravitons exist, that click, at that moment, at that frequency, is overwhelmingly likely to be a single graviton, absorbed. The choir tells you when to listen. The bar hears the single voice. It is worth pausing on what, physically, the bar would be registering, because the delicacy has no precedent anywhere in measurement. The energy of one absorbed graviton, at that frequency, spread into a 10-ton cylinder, is about 10 to the minus 31 joules. That is roughly the energy it would take to lift a single bacterium by a small fraction of the width of an atomic nucleus. The proposal is to notice, reliably and on demand, an energy deposit of that size, in an object the mass of a school bus. And notice, too, the quiet act of historical repair folded into all this. If a resonant bar one day catches the first single graviton, then Joseph Weber, the man remembered for hearing things that were not there, will have been not wrong about the instrument, only early, by 2 technological generations. His bars could never have heard a classical wave at realistic strengths, but the instrument he invented, chilled 1,000 times colder and read out with quantum eyes he never lived to see, may end up hearing something far stranger than what he sought, a single quantum of the thing itself. Science does sometimes circle back to bury its embarrassments with honors. So picture it, some night in the 2040s or 50s, because this is now a scene that can be pictured without apology. A laboratory after midnight, somewhere quiet. At its heart, behind nested shells of steel and vacuum and suspension, hangs a dull grey cylinder, 10 tons of niobium, holding a temperature no natural place in the universe has ever known, its atoms stiller than stillness, its great body poised on the bottom rung of its quantum ladder. Screens in an empty control room breathe with slow data. On the far side of the planet, an interferometer's alert flashes outward across the network. Automatic, routine, wave passing, 175 Hz, 2 black holes, 1.4 billion light-years. The alert reaches the quiet laboratory. And in that same slice of a second, in the cold, the cylinder, touched by something no instrument in history has ever isolated, rises by one indivisible step, and a single number, on a single screen, ticks from 0 to 1. That is the whole event. No flash, no thunder, one quantum of sound, in a frozen bell. The missing 3rd chapter of the gravity textbook, waiting on a first sentence. And this, at last, might be its opening word. And now I have to tell you why. Even then, with the click on the screen and the champagne open, the story would not be over. Because there is a hole in this beautiful plan, and it is not in the cylinder, or the cold, or the coincidence. It is in the year 1905. The hole has been sitting inside the photoelectric effect, inside the founding legend itself, for 120 years. And it is time to go back and look at what Einstein's famous proof actually proved. Let's return, as promised, to the vending machine. Hours ago, at the start of the night, we told the founding legend of quantum physics, the way every textbook tells it. Light below a threshold color cannot eject electrons from metal, no matter how bright it blazes, because an electron must be paid in a single coin, and small coins never add up. Einstein read that behavior as proof that light comes in packets, The packets became photons, the photons became the template for every force's messenger, and the Nobel Committee filed the matter as settled. The photoelectric effect proves the existence of the photon. Generations of physicists were raised on that sentence. It is carved, in effect, over the door of quantum mechanics. And it is not true. Not quite. And the not quite is about to matter enormously. The flaw was made fully explicit in 1968 by Willis Lamb, a Nobel laureate himself, together with Marlon Scully, in a paper whose title was its whole thesis, The Photoelectric Effect Without Photons. What Lamb and Scully demonstrated was quietly devastating. Take the metal plate seriously as a quantum object, electrons living on discrete energy levels, which by 1968 was beyond dispute. But now let the light be a completely classical wave, smooth, continuous, chunkless, exactly the picture Einstein supposedly demolished. Run the calculation honestly, and out comes the photoelectric effect. All of it. The frequency threshold, the instant ejection, the energy of the electrons tracking the color and not the brightness. Every feature that the legend attributes to packets of light is reproduced, in full, by a smooth classical wave washing over quantized atoms. The reason is subtle and beautiful. A classical wave oscillating at some frequency can only drive a quantum system between levels separated by the corresponding energy step. It is resonance, not chunkiness. The threshold behavior lives in the receiver, not in the light. The vending machine analogy was always backwards. It was never that the light came in coins. It is that the electron's exit turnstile only accepts one denomination, and a smooth flow of the wrong denomination, however torrential, cannot turn it. Understand what this means about history. The photoelectric effect, the experiment that won Einstein his Nobel Prize and founded the quantum theory of forces, demonstrated the quantization of matter, which nobody had doubted for decades. It never demonstrated the quantization of light. Einstein's conclusion was correct. Light is made of photons, but the experiment on which the legend rests could not, even in principle, have established it. So how do we actually know photons exist? Because physicists eventually found effects that no classical wave can fake, and they are effects not of energy, but of statistics, of the pattern of clicks, rather than the existence of clicks. In 1977, a single atom was watched fluorescing, and its photons arrived one by one, with a telltale hesitation between clicks, anti-bunching, impossible for any smooth wave, which always bunches. In 1986, single photons were sent one at a time onto a half-silvered mirror with a detector on each side, and the two detectors never clicked together. A classical wave splits and triggers both. A photon is indivisible and must choose. Click here or there, never both. That whisper of never both, that statistical silence, is the actual experimental proof, delivered 81 years after Einstein's paper, that light is grainy. The photon was hypothesized in 1905 and proven, in the strict sense, in the 1980s, within living memory, while the textbooks continued printing the legend. Now carry this, carefully, like a candle, back to the frozen cylinder. The gravitophononic detector is the photoelectric effect restaged for gravity. That is its glory, and, you can now see, its exact limitation. The bar's click tells us a quantum of sound was born in the metal at the moment a gravitational wave passed. But Lamb and Scully's ghost asks the question it asked in 1968. Who was quantized, the wave or the bar? A perfectly classical gravitational wave, Einstein's smooth ripple with no gravitons in it at all, oscillating at the bar's resonant frequency, can also drive the bar up one phonon step, by pure resonance, the smooth flow turning the single denomination turnstile. The click happens either way. If gravitons exist, the coincident click almost certainly is one, but the click alone cannot prove they exist, because a graviton-free universe produces the same click by classical means. The bar, in the strict logician's sense, would give us the graviton the way 1905 gave us the photon. A discovery in every practical sense. Front pages, champagne, a Nobel Prize before the decade was out, and a century of textbooks calling it the day the graviton was found. And buried in the fine print, known to the careful, the same asterisk as before. Consistent with, not proof of. To prove the field itself is grainy, you need what the photon needed: statistics. Correlations no classical wave can fake, and that requires gravity prepared in a non-classical state, the gravitational analog of single photon light, and nature, as far as anyone knows, manufactures no such thing. Colliding black holes make enormous coherent floods, the most classical gravitational states possible. Nobody has the faintest idea how to make a single graviton state to order. That is the far wall of this subject, and it is still standing, and it may stand for centuries. But between the click and the proof, there is a middle country, and in 2025, a proposal appeared for exploring it with tools that mostly exist. Ralph Schutzhold, a theorist in Dresden, published in Physical Review Letters a scheme he describes as an optical Weber bar, and the phrase is chosen with a smile: no metal, no millikelvin cylinder. The resonating body is light itself. Picture a racetrack for laser pulses, an interferometer on the kilometer scale in which a pulse of light is split and made to bounce between mirrors up to 1,000,000 times, folding the path into an effective journey of about 1,000,000 kilometers, more than twice the distance to the moon, all within apparatus that fits on the Earth. When a gravitational wave rolls through LIGO, it stretches the arms only while it is passing. The phase shift, it writes, is transient, gone when the wave is gone. Schutzhold's geometry is arranged so that the interaction leaves a permanent mark. The passing wave transfers a tiny but lasting quantity of energy to the circulating light, shifting its frequency by a hair, and a second stage of the interferometer, comparing the pulse against its twin over the long folded path, accumulates that hair's breadth shift into a measurable phase difference that persists after the wave has departed. The light comes out of the encounter changed, and stays changed, an odometer rather than a speedometer. In the language of quanta, what the light has done is undergo stimulated absorption of gravitons, or, run the other way, stimulated emission. The same physics that makes a laser laze, now written with gravitons in the role of the medium. Even at its baseline, hear how the ambition has shifted. This is no longer only detecting gravitational waves. It is exchanging book-kept energy with one, the first proposed act of manipulating gravitational radiation, rather than merely witnessing it. And the baseline version, Schutzhold argues, is plausibly within reach of present-day laser and mirror technology. But it is the upgraded version that aims at the far wall. Feed the interferometer not ordinary laser light, but light in a strongly non-classical state, the exotic superpositions physicists call noon states, in which many photons behave as one indivisible entity, and energy conservation does something profound. It ties the quantum state of the light to the quantum state of the gravitational wave that fed it. Measure the photon's statistics, and you are reading, indirectly, whether the gravitational field itself can occupy quantum superpositions. If a gravitational wave can be steered, even slightly, into a genuinely quantum state, then gravity is quantum, and the argument is over, forever. That is the actual doorway to the actual proof. The catch is honest and large. The biggest photonic noon states ever built hold about 5 photons, and this scheme would need orders of magnitude more, so the far wall recedes from impossible to merely generational. But notice what has happened to the shape of this story. The photon needed 81 years to get from its click to its proof. Gravity now has, on paper, both halves of that same journey mapped. The click machine in the frozen cylinder, the statistics machine in the folded light, and neither map contains a black hole. And for completeness, There is a third road on the modern map, one that sidesteps the catching problem altogether. A family of tabletop proposals, mentioned briefly earlier tonight, aims to place two microscopic masses in quantum superposition close to one another and check whether gravity, and gravity alone, can entangle them, weaving their fates together in the way only quantum interactions can. No classical field, however cleverly arranged, can create entanglement. That is a theorem, not a hope. So if two masses ever walk out of such an experiment entangled by nothing but their mutual gravity, the field's quantum credentials would be certified without a single graviton ever being caught, the way you might prove a stranger speaks a language by watching two of their letters agree, without ever hearing their voice. Those experiments face their own decades of struggle, chiefly the fantastic difficulty of holding anything heavy enough to gravitate in superposition long enough to matter. But they belong on the same short, precious list as the cylinder and the folded light, the list of doors that the universe, so far as anyone has proven, forgot to lock. The night began with a lecture proving 4 roads ended in walls. It ends with 2 new roads, neither one forbidden. What remains is to gather everything we have carried, walk back to the beginning, and finally answer, plainly, the question in the title: what exactly is incomplete about the gravity you were taught, and whether that incompleteness is a wound, a warning, or, as I will try to persuade you in these last minutes, something closer to a gift. So let's answer the question. It has been waiting all night, patient as the drizzle of gravitons through the roof, and you have earned the plain version now. Why is everything you were taught about gravity incomplete? Not because your teachers were careless, and not because Newton or Einstein were wrong. Nothing you were taught was wrong. The apple falls exactly as Newton said, the starlight bends exactly as Einstein said, and the clocks in orbit drift exactly as his geometry demands. The incompleteness is of a different and stranger kind. You were taught a force, and then a geometry, and you were never told that the geometry has never been reconciled with the deepest fact we know about this universe, that everything in it, examined closely, is quantum. 3 of the 4 forces have taken the examination and produced their particles, their receipts, their clicks in the dark. Gravity has never taken the examination. Its hypothetical quantum, the graviton, named in 1934, characterized down to its spin and its speed, required by every road to a final theory, has never once been observed, and there exists no measurement, anywhere in the scientific record of our species, that certifies whether spacetime is smooth or grainy at the bottom. The 3rd chapter of the Gravity book is not hidden from you. It is unwritten, for everyone, and that is the honest state of human knowledge as you lie there tonight. The 2 most successful theories in history, each verified to a dozen decimal places on its own ground, have never been introduced, and the introduction depends on a particle that may be unobservable in principle. That is what was left out of your education, not an answer, the existence of the question. And why is the chapter unwritten? Here the night has given us something better than an excuse. It has given us a pattern. Follow any road toward a single graviton, and the universe meets you with a wall, and the walls are not random rubble. The mirror route died when the uncertainty principle, quantum mechanics' own signature law, conspired with general relativity's own signature object, the black hole, to swallow the measurement. The conversion route died when the quantum vacuum, the foundation of field theory itself, shattered into sparks at exactly the field strength the trick required. The other routes drowned in gravity's weakness and the neutrino fog, with the same absurd number, 10 to the 36, 10 to the 34, stamped on every verdict, like a signature at the bottom of every page. Hold the pattern up to the light one last time, and notice, with the particular chill this fact deserves, what the walls are made of. Every barrier hiding the quantum of gravity is built from quantum mechanics and gravity. The The two theories whose marriage the graviton would seal are the same two theories that stand guard, together, at every door of the church. Perhaps that is a coincidence of scales, nothing more, the accidental architecture of a universe that owes us no viewing gallery. Or perhaps the structure of the censorship is itself the final clue, and the two rulebooks defend the room where they merge, because what is inside that room is the writing of both. Nobody knows. Dyson thought the concealment might be telling us the marriage never happens. The builders of frozen cylinders think it is telling us to knock more cleverly. The universe, so far, declines to comment. But here is what the last act of the night established, and it is the reason I promised you, hours ago, that the ending would be more hopeful than the middle. The concealment is not total. Dyson's four walls were real, and his arithmetic stands unrefuted. But his map, it turns out, had edges. The quantum sensing bar walks around the mirror trap by making the catcher's quantum 10 tons heavy. The folded light of the optical Weber bar walks around the conversion trap with no doomed magnetic field anywhere in the design. The entanglement experiments skip the catch entirely. None of these roads is forbidden. All of them are brutally hard, a millikelvin colder than any large object has ever been, quantum states larger than any ever prepared, and any honest accounting says decades, plural, with failure fully possible. But decades are not geological ages, and hard is not impossible, and the difference between those two words is the entire moral of this story. In 2012, it was reasonable to believe the question was closed. In the 2020s, quietly, in a handful of papers, it reopened. Out of sight, it turns out, was never the same as out of reach. And there is one more consolation, the deepest one, for anyone who feels the ground has gone soft under a childhood certainty. The incompleteness you have been listening to all night is not a flaw in physics. It is physics, seen honestly, in the middle of its work. Every generation is handed a book with a missing chapter, and the missing chapter is precisely where the future lives. A century and a half ago, atoms were the undetectable fiction, dismissed by serious people as metaphysics, until a patent clerk counted them by their jittering. A century ago, the neutrino was the undetectable ghost, apologized for by the man who proposed it, until it rattled a tank in South Carolina 26 years later, and today we build telescopes out of Antarctic ice to catch them by the thousands and read the sky by their light. The undetectable has a way of becoming, first, barely detectable, and then, eventually, an instrument. If the pattern of 2 centuries holds, the graviton's click will come, some cold night in some quiet laboratory, within the lifetime of someone listening to this. And when it comes, it will not close the book. It will do something better. It will start the chapter whose absence you now know how to feel, the chapter about what space and time actually are, written at last in the only ink physics accepts, which is evidence. If you want a compact way to hold the whole night in your hand, know that everything we have covered sorts the world's physicists into 3 quiet temperaments, and all 3 are being honest with the same facts. There is the pessimist's reading, Dyson's reading, which takes the walls at their word. The universe censors its own foundations. The graviton is unobservable in principle, and quantum gravity may be a question grammar allows but nature does not, a sentence that passes and points at nothing. There is the engineer's reading, the reading of the cylinder builders, which notes that only 2 of the 4 classical roads were ever truly forbidden, that the others were merely priced beyond a young civilization's means, and that the 2020s proposals have already negotiated the price down by orders of magnitude, from star systems to laboratories, from geological ages to careers. Walls on this reading are what the frontier always looks like from below. And there is the epistemologist's reading, the long historian's reading, which points out that this is simply what proving a quantum takes. The photon needed 81 years to get from its famous click to its actual proof, and nobody now remembers that stretch as a crisis. Gravity is at the beginning of the same long road, running the same sequence, click first, statistics later, and the only unusual thing about the graviton is that we can see the whole road drawn in advance. 3 readings, 1 set of facts, and the beautiful thing is that the instruments now being designed will eventually retire 2 of them. That is what makes this moment, the one you are falling asleep inside, quietly historic. For 90 years, this subject had no possible verdict. Sometime in the coming decades, for the first time, it will have one. So let the picture you fall asleep to be this one, the true one. You, in your bed, held gently against the mattress by the curvature of space-time, or by the exchange of countless unseen messengers, and the honest answer is that no one alive knows which sentence is the deeper truth. Around you, through the ceiling and the blankets and your own quiet body, the sun's gravitons falling in their eternal drizzle, 4 per square meter per second, untouched and untouchable, carrying the universe's most closely guarded secret through your room at the speed of light. Somewhere ahead, in a decade with a number you will recognize, a cylinder colder than the space between galaxies, waiting for a wave from a collision older than your species, and a single step on a quantum ladder, and a number ticking from 0 to 1. Everything you were taught about gravity is true, and everything you were taught about gravity is incomplete, in exactly the way a story is incomplete on the night before its best chapter is written. Thank you for spending this night with me, walking the long way around the missing particle of gravity, from a paperclip on a table to a frozen bell waiting for a click. If this kind of unhurried journey through the edges of what we know is how you like to fall asleep, a quick like, or a subscription if you have not already, would mean a great deal to me. It is a small gesture on your end, and it is what lets me keep making these long, slow explorations. And remember, the next time you feel your own weight settle into a chair or a bed, that the force holding you there is the one force in this universe still keeping its deepest secret. Good night, and may you never feel gravity's quiet pull the same way again.